Hi everyone. Before we get to systems, let's talk about some legal moves or operations when we solve one single equation in one unknown. Take 2x minus 1 equals 5. What are some legal moves or operations? We can add 1 to both sides of an equation, and we get 2x equals 6. And then we can divide both sides of an equation by 2, and we end up with x equals 3. Remember, the answer to solve an equation problem is technically a solution set. It's the set consisting of the sole solution, 3. Now notice that the solution set applies to all 3 of these equations. 3 is the only value for x that will work in all 3 equations. And all 3 of these are equivalent equations. These are equivalent equations because they have the same solution set. In a way, they have the same graph, x equals 3. On the number line, x equals 3. Kind of like when we checked for equivalence back in trig. So the idea here is that you write a sequence of equivalent equations with the same solution set until you get a really nice equation whose solution set is obvious. At this point, x equals 3. It's obvious that 3 is the only real value for x that will make this equation work. In your Algebra 1 class, if you got up to x equals 3, you're basically done. But now in pre-calculus, we do want you to write the solution set. But really, this is obvious from this. Now, with systems, it's the same basic idea. Equivalent systems have the same solution set. This time, the solutions will be more like ordered pairs or ordered triples. And what are the legal moves or operations? They're called elementary row operations. I'll abbreviate them EROs. These are categories of legal moves or operations that allow us to write a sequence of row equivalent matrices, which correspond to equivalent systems, meaning they all have the same solution set. The idea is that we write equivalent or row equivalent matrices until we obtain one whose corresponding system and whose corresponding solution set is easy to find. By the way, the symbol for row equivalent matrices is this tilde or squiggle. So if an augmented matrix A is row equivalent to an augmented matrix B, we use the tilde or squiggle here to indicate row equivalence. It means that the system that A represents and the system that B represents are equivalent. They have the same solution set. That's different from equality. We'll talk about that later. So what are the 3 categories of legal EROs? And there are different ways to name them. One legal category of moves is row reordering or row switching. For example, if you have a system with these 2 equations, well, this system has a solution set. Solutions are of the form parentheses x comma y. Will the solution set change if you switch the order of these equations? No, we're looking for simultaneous solutions. It doesn't matter what order these equations are in. As far as maintaining the solution set goes. So you may as well switch these 2 equations and you'll end up with the same solution set. Your solutions will not change. xy works here if and only if xy works here. Which means when we do our augmented matrices, we can switch any 2 rows. In fact, we can permute the rows in any order, but make sure that each row here is represented in each row here. Make sure that each row here is represented in a row here. Don't miss any rows. Okay. So the augmented matrix for the first system looks like this. It's legal to switch the rows, and then you get this row equivalent matrix over here. Again, the symbol for row equivalence is this tilde or squiggle. We can reorder the rows of an augmented matrix in any order. And it's good to indicate what kinds of operations we're performing. So for example, if you're switching rows 1 and 2, it's really good to indicate that somehow. For example, books might do something like that. But you can pick whatever notation suits you well. Ideally, a notation that will inform a reader, like your grader or professor. In fact, on an exam, I tell students to write these kinds of notations so that it helps both the student and me to know what the student is doing if I'm not sure what the student is doing with the numbers. Especially if a student gets a problem wrong, I like to check the work, and this helps me a lot. Because imagine looking at a page full of numbers and not being given any instructions. It's like programming code with no comments. It's like, what are you doing? It's really good to indicate what you're doing. Do not reorder columns. Then you're mixing up the variables. You can reorder rows, but not columns. Row rescaling. We've seen something like this before. Let's say you have 1/2 x plus 1/2 y equals 3. You're itching to get rid of these fractions. How can you do it? Multiply both sides by 2. It's still legal. Okay, so if you do that, then you get this equivalent system over here. Same solution set. When you consider augmented matrices, we can multiply or divide through a row by any non-zero constant. Don't multiply by 0. So the first augmented matrix looked like that. It's legal to multiply the first equation, or the first row, by 2. Don't forget the right-hand side. If you tend to skip the right-hand side, maybe you shouldn't put the slash there. You could use notations like these. Replace the row 1, replace the old row 1. Okay, sorry. To get the new row 1, take twice the old row 1. To get the new row 1, take twice the old row 1. So 1/2, 1/2, 3 becomes 1, 1, 6. You can rewrite the second row. We often rewrite rows in this section. Be prepared for that. And we have row equivalents. Now, this third category, there's not a good name for this. Some books say row replacement. Well, aren't we always replacing rows? Some books, or I might say the row addition method, maybe. Basically, the idea is we can add a multiple of one row to another row. Basically, it combines row addition and rescaling. We can add a multiple of one row to another row, and we get a row equivalent matrix. For example, consider this system. When you write down the augmented matrix, it looks like that. Now, it turns out that when we perform our Gibbs method in just a moment, we love having that 1 in the upper left-hand corner, and we want to eliminate down. By eliminate, what do you think I want to put here instead of a -2? I want to see a 0 there, but we're going to have to deal with these other entries. All right, so what do? To kill the -2, I'd like to add a multiple of row 1 to row 2 so that the -2 becomes a 0. What should I multiply row 1 by before I add to make that a 0? I say double the first row, like before. Multiply the first row by 2. I like to do it in column form. So twice row 1 is 266. I'll put that in the middle row. Okay, we're changing row 2, right? We're changing row 2. So since we're changing row 2, I'll put the old row 2 up on top, which is the -2, 5, 16. The old row 2 goes on top, -2, 5, 16. Then twice row 1, 266 over here. And then to get the new row 2, you add. Remember, you can multiply by a negative number if necessary before you add in order to make a 0. Remember, just like with long division, it is much, much easier to add than to subtract. Like with long division, like with vectors, it's much easier to add than to subtract. -2 and 2 gives us 0. We like that. I'd put a smiley face here. Hard to draw smiley faces. Here, 5 plus 6 is 11. Here, 16 plus 6 is 22. Don't forget the right-hand side. Now, normally, we keep this row that we're rescaling by. We keep the old row 1, the 1, 3, 3. We like the 1 there. We like that. But then we replace the old row 2 with the new row 2, 0, 11, 22. And take a wild guess. What do you think we want here? What do you think we like having on the main diagonal? We like having 1s. We like that coefficient, which means we're going to do what with row 2? You're not allowed to subtract numbers through a row, but you're allowed to divide. We're going to divide by 11, or multiply by what? 1/11. Some books like to think of it that way. All right. And again, we have row equivalent matrices here. They're not equal. They don't have the same entries in the same position. Those are equal matrices, but these are row equivalent matrices. They represent equivalent systems. We use this tilde. Next up, we're going to look at GEBs, a technique that will allow us to solve linear systems of equations using augmented matrices and EROs.